Alright, in our last video we were going over the properties of fractions and we stumbled upon having to have, let's say, a over c plus b over c. So we noticed that they had to have the same denominator. Okay. So one method of achieving the same denominator is to use prime factorization. Okay, and I'll show you why in a second. So prime factorization is one of my most favorite things to do in algebra, just because it has so many different uses if you're creative enough, or if you can see it, or if you can learn to use it, which is what the whole point of this series of videos is to show you little things that they necessarily don't teach you in class or in school or even self-study, but I've noticed, and they're actually pretty helpful for algebra and calculus and anything else. So prime factorization, okay, is also known as the factor tree. Right? You may have learned in elementary school, middle school, wherever it was, and you take a number, let's say 36, any number, it could be any number, and you break it down into its prime factors. So 36 is 6 times 6, okay? 3 times 2, okay? 3 times 2, okay? And here we have the factor tree, okay? So factor tree, even to illustrate that even further, okay? We have green here as in a tree, and you have your little apples in the end. And this is your factors, okay? Your prime factors. So your prime factors for 36 is 3 times 3 times 2 times 2, right? 3, 3, 2, 2. Right? Or 3 squared times 2 squared. Or 9 times 4. You see, they are all equivalent. And this is why prime factorization is so useful in algebra. Okay? So let's say we're given the fraction 5 over 36 and we have to add 7 over 120. Okay? How would we be able to find what's called the least common denominator? Okay? Well, we can do 120 times 36. Okay? If we use the properties of fractions that we learned in the last video. Right? But I mean, that's a really large number, right? Could you do that easily? Would you be able to do that under a time crunch? Okay? Instead, what you could do is you could make a factor tree of each. So you take 36, we're going to rewrite it over here. Okay, 6, 6, 3, 2, 3, and 2. Okay. And then you take 120 and do the same thing. 12 and 10, 5 and 2, 6 and 2, 3 and 2. Okay. So, why? 10 times 12 is 120. You can see that. 5 times 2 is 10. 6 times 2 is 12. Right? And 3 times 2 is 6. Okay? And then we're going to identify our prime factors. So the prime factors of 36 is 3, 3, 2, and 2. We're going to write those down. 3 times 3 times 2 times 2. Those are the prime factors of 36. The prime factors of 120 are 5, 3, right? 5, 3, 2, 2, 2. 2, 2, 2. So, how can we use this to find the least common denominator so that we can easily add two different fractions? Well, 3 squared times 2 squared, okay, the same, right? That's 36. And then 5 times 3 times 2 cubed. So you see, all I'm doing here is we're taking this, okay, and we're just going to combine, right? So 2 times 2 times 2 is the same as 2 cubed, right? Just as 2 times 2 is the same as 2 squared, and 3 times 3 is the same as 3 squared, okay? Now, if you have the same intuition that I did when I saw this, you can see that if you combine 3 squared, okay, times 2 cubed times 5, you get a factor that they both have in common. Okay? Now I'm going to explain why that works. Okay? So, if you don't see it intuitively, right, you have 3 here, Okay? But you have a 3 squared over here. Right? So the only way that it would be divisible is if you have the highest power of each. So to find the least common denominator easily, okay, you take the highest power of each factor, okay? So let's do 3 squared. Now, is the highest factor of 2 squared? No, it's cubed over here. So you multiply by cube, alright? And then you take 5 because it's unique. And 3 you already did. You already did it with 3 squared. Right? So if you multiply this out, you get 9. Okay? 2 cubed is 8 times 5. Okay? Do 8 times 9. Okay? Times 5. You get 360. Okay? So you want to check that real quick. 40 times 9, 40, which is 8 times 5. Okay? 9 times 0, 9 times 4 is 36, 360. So we take this and we set both fractions, okay, over 360. Let's move back up here. Remember we had 5, and we had 7. Okay. Now, our original here, let's get rid of all this clutter. Okay. We're going to get rid of all this clutter. Okay. Our original here, we're setting them over 360. Okay. 36 and 360, you have to multiply it by 10. Now, since we multiply the bottom by 10, we must multiply the top by 10 as well. So you get 50, right? 10 times 5 is 50. 120 and 360, to get that, we must multiply by 3. So it'd be 7 times 3. 21. Combine these two, you get 71 over 360. And that is why prime factorization is infinitely useful. Okay? Now, let's continue over here. A second case where prime factorization can be used. Okay? So, reducing now. Okay? So let's move back up to this here. Okay? Yeah, 5 times 10 is 50, 7 times 3 is 21 over here, right? Add these two together, you get 71. Now, can you easily see if this can be reduced? Right? Well, if you can't, use prime factorization. So let's take a different problem. Let's take an easy problem to see. Okay? You can reduce this pretty easily in your head, right? But if you couldn't, if it was a more difficult problem, right? You take the prime factorization, 120. We know that this is 10 and 12. Okay? 6 and 2, 5 and 2. Okay? And then 3 and 2 here. And these are the prime factors of 120. Okay? So let's rewrite them. 5, 3, and then 2 cubed. Remember? Because you have 3 2's. And 3 and 5 are unique. They're by themselves. Okay? This is equal to 120. Now, we do the same for 360. 10, 36. We get 5 and 2. Okay? 6 and 6. 3 and 2. 3 and 2. Okay? So now we're going to rewrite this over here. 5 is unique. 3 is unique. Get rid of these. Excuse me, 3 is not unique. There's 2 3's. Squared. And then 2 cubed. 2 cubed. Now, how can you use this to easily reduce a fraction? Well, leave it in its prime factors, okay? So if we go back to the original, it was 120 over 360. So it would be 5 times 3 times 2 cubed, right? Because we showed here that it's the same. It was prime factorization, okay? Over this here, because this is equal to 360. Now we can immediately see what cancels out if you remember the properties of fractions. We go back to that real quick. Okay, is the same as, you cancel each other out, a over b. So we have a 2 cubed on top, top, excuse me, a 2 cubed on the bottom, a 5 on the top, and a 5 on the bottom. They all cancel out. You have 3 over 3 squared is the same as 3 over 9 or 1 over 3. 3 goes into itself 1 time, 3 goes into 9 3 times. And now we were able to take this here and get 1/3 very easily. So one could see almost immediately that it's 1/3. But if you have really, really difficult, crazy numbers, and you're going to have to reduce it without a calculator, how do you do it? Prime factorization. A third case where prime factorization is very, very useful. Okay? Factoring. Okay? We're going to explore factoring later on in the video series, but for now, let's do a very simple factor, okay? And someone tells you, factor this, please. Okay? So, to factor this, right, we use prime factorization. If you're not immediately sure which factors of 36 give you 5 when added, use prime factorization of 36, get 6 and 6, 3 and 2, 3 and 2. Okay? And then you can start combining. You can say, oh, okay, we can combine here, 6, here, 6. It's the same as 6 and 6. Or it's the same as 3 and 3, 9, and 4 and 4 times 4. That didn't work. Oh, look, here it works. Right? And we got it because, okay, 3 and 2, 3 and 2. We combine these two 3's here, 9, and we combine these two 2's here, 4. We can see pretty easily that if you take here these two factors, right, you're going to get the answer to this problem. Okay? X plus 9, x minus 4 equal to 0, right? And we saw that through prime factorization, right? So we can check that. X squared minus 4x plus 9x negative 36. Okay? These two are equivalent. Right? X squared minus 4 plus 9, okay, plus 5x minus 36. And those are some of the few uses of prime factorization. As we go through the video series, when I find a new use for it, or remember one, I'll go ahead and bring it up. But it's a very useful skill to learn, and it's pretty simple. Now, it may have seemed long. I was trying to go with a slow explanation, but that's prime factorization.